Okay, so Alexander, I suggest we start smoothly. I'll start from just introducing briefly our small list of rules. So there are only a few rules. In order to ask a question to the speaker, please either raise your hand by pressing the raise hand button in the participant list, or just type your question in the chat. So, and in case you have a question, I will try to stop Alexander at the proper moment and turn on your microphone. So during the talk, as far as I know, your microphones will be kept turned off just in order to avoid any misuses. So, okay, this is, first of all, welcome back to our optical seminars after some summer break. And in order to, as a courtesy to the speaker, please enter your full name. Yes, I think everyone is entering their full names right now. Thank you very much for that. And some self-promoting. This is optical seminar, which is held by the Physics and Engineering Department of ITMO University. And with that, I would like to start our seminar. It's my great pleasure to introduce our today's speaker, Aleksandr Bogucki from University of Warsaw, Poland. And today he will be giving a talk on applications of direct laser writing for optical studies of semiconductor nanostructures. Aleksander, please, the stage is yours.
So thank you very much for your introduction. And yeah, so maybe at the beginning, when maybe we are waiting a little bit more for other participants, so I will just tell you a little bit about our faculty, a very small part. So I'm from Laboratory of Ultrafast Magnetospectroscopy, and the work presented during this seminar was the result of collaboration between this group, Laboratory of Ultrafast Magnetospectroscopy and Photonic Nanostructure Facility, which are both located at the University of Warsaw, Poland. And so our group, ultrafast magnetospectroscopy, so it usually means that we are in a darkness and we are measuring optical stuff. So that's why, and this is the photo of our laboratory. So we often have some strange colors in the laboratory, because if you are measuring in some spectral range, then we don't want to have some unwanted light from lightning in our laboratory. And so yeah, this is our research group. So there are a lot of people, and we are mostly interested in topics which are listed here. So our origin as a group are diluted magnetic semiconductors. As we are specializing we are specialized in quantum wells with diluted magnetic impurities like manganese, cobalt, iron, and stuff like that. So yeah, we are producing quantum wells, but also quantum dots containing single magnetic impurities. So this is the area of solotronics. But now we are also interested in this emerging new materials like 2D materials, so transition metallurgical cogenites, not on the most popular one, but also a little bit less popular, like antiferromagnetics, like listed here, manganese, sulfur phosphide. We have some studies about graphene also, optical, like double color pump probe. And part of our group is also interested in light matter coupling. So in polaritons and interaction between quantum wells, light, polaritons, and also because we like magnetic ions, so also with magnetic impurities inside. And so the biggest advantage, I guess, of our group is that part of it is the MBE laboratory, so molecular beam epitaxy laboratory, So we can produce samples ourselves and then characterize it on site. So the time from producing the structure and then characterization of the structure, it's very short, few hours or 1 day, stuff like that. So we can quickly, in the same growth condition, improve the samples and design. And so, yeah, we are basically producing all of mentioned materials and structures. And we are, yeah, for example, our latest achievement that we are pretty proud of, it's we show that we can produce large scale, so in molecular beam epitaxy, monolayers of molybdenum selenide, and which is, yeah, what was most important for us, it has very sharp emission lines in photoluminescence, so we can resolve spectral lines. And what is also important, it is the homogeneity of such lines. It's much better than homogeneity of exfoliated one. So let's say in terms of future applications and some commercial usage and bigger scale, that was quite interesting to find out how to grow these materials. So all of these listed materials. So here are some highlights on exactly this topic. So when the topic was under this, so quantum dots, and here's some example from quantum dots so far. Yeah, so that's it. So this is background, and now I would like to thank all the people that contributed directly to that work. So there are also people from different units, like from Japan and from Grenoble, from France. And last but not least, of course, the acknowledgements. That thank you for money. Okay, and so now I think it's a good time to start. So once again, application of direct laser writing for optical studies of semiconductor nanostructures. So in fact, I will be talking about type of lithography. So this is basically laser lithography, what I will be covering today. And because I'm from semiconductor background, when we are thinking about lithography, so when we are thinking about lithography, then the definition of lithography from Greek lithographos means that we are writing in a stone, right? So we are thinking rather about flat structures, like here we can see this silicon wafer with some structures etched on it, fabricated. Or when we are thinking about electronic devices or integrated circuits. So basically, yeah, they are kind of 3D structures, but rather we are thinking about planar structures. And what is really special about this direct laser writing and this technique that I will introduce to you is that you can, yeah, produce things that are definitely not planar as well. So here is an example of some fancy object which is absolutely not planar, has fine details which are below 1 micrometer. So these parts here are below 1 micrometer, but the overall structure is pretty large in that comparison. Yeah, you can print whatever you want, so some funny stuff, or even a statue of a person with an incredible amount of details. So yeah, how it's possible? So how lithography could go as far? So this is thanks to the two-photon polymerisation, and yeah, this is type of 3D lithography. So let's start with let's say our first ideas. So we are rather used to subtractive manufacturing. Nowadays, it starts to be changing thanks to the 3D printers. But usually, when we are thinking about producing some part, we are going to our sheet or other place. When we ask our technicians to manufacture something, they have as a some cube of material like aluminum or stuff like that, and they use subtractive techniques like milling, drilling, cutting, chopping, stuff like that. And as a result, we can obtain pretty complicated object and a lot of waste, because yeah, we are basically removing that material, which is then not in a nice usable form of cube, so then we need somehow recycle it. So totally, and this approach in nanoscale and in semiconductor devices is represented, for example, by focused ion beam, where when ions of gallium are projected onto the sample surface, and because of that they kick off some atoms, and because of that we can obtain pretty impressive structures like here, when it's combined with another subtractive manufacturing technique like wet etching. So you can obtain very, very small bridge. Here is 45 nanometers wide. And of course, yeah, we can produce things like micropillars. This one are produced at our faculty. And as you can see, yeah, there are 2 quantum wells and distributed Bragg reflectors on both sides and in the middle of that. And yeah, you can think that there is flat surface outside, but in fact, to obtain such a smooth sides of this micropillar, yeah, you need to be quite smart. And here is the top view of the same micropillar, and here, as you can see, nothing is smooth. So it's quite brutal technique, and there are a lot of dislocations, imperfections now on this, around this beautiful micropillar. So yeah, it's the matter of making photos, right? So this picture is nice, but this one is the truth. So so people are also looking for less destructive techniques and less invasive techniques. So we are not wanting to kick off atoms, but rather is it possible to add atoms. So of course there are additive manufacturing techniques. So yeah, nowadays commercially available regular 3D printers when you add just melted plastic on top of, but the resulting size of structures is quite big. But in nanoscale, of course, MBE is an example. So molecular beam epitaxy is an example of some additive manufacturing when you're adding layer by layer on top of the substrate. And so this direct laser writing is another example of additive manufacturing. And so how it works. Here you can see we have a substrate. This is an example of 1 inch substrate or 2 inch. Okay, doesn't matter. But you pour the resin photoresist on top of it. So this is usually it's enough just to put 1 small droplet on top of it. So like here. So we use IPL photoresist, but there are plenty of available photoresist on the market with different properties. This photoresist is on top of cover glass, microscope cover glass, and is mounted on piezoelectric stage. And by using laser, femtosecond laser, 780 nanometers, in the focus of the laser, polymerization occurs. So this photoresist becomes a solid polymer. And by moving you can move both things. So you can move of course the laser beam, or you can move the substrate, and by that you will obtain this polymerized trace, so this solidified photoresist. And it's only solidified in small region when the power of laser is sufficient to, so it's above the threshold of polymerization. So, and to increase, let's say, the resolution of such printing, it is used this process called two-photon absorption, which everybody probably knows. But what is quite important, how it improves the resolution. So here is the container with dye. It's I don't remember, but probably rhodamine or another organic dye solution. And from the left side, it's excited with 405 nanometer laser. And as you can see, this photoluminescence comes from quite large area. Even the focus point is somewhere here. From the other hand, on the right side, it's excited with 800 nanometers, and as you can see, the only photoluminescence occurs in this very small area, and that's because the two-photon absorption is proportional to the square of the power, and when we have Gaussian beam, then we obtain the lateral size, which is depends on the fourth power of the characteristic scale of the beam. So we obtain the increase in resolution. So the smallest polymerized volume is called voxel. This is like a pixel, but in three dimensions. So here are some scanning electron microscope photos of, let's say, destroyed structure. And here you can see this ellipsoids, elliptic-like shapes. And so these are polymerized voxels. And yeah, this voxel has shape of ellipsoid. And in our case, when we use this wavelength of laser, it's usually 1.2 micrometer in height and 420 nanometers width. But what is quite important, the resolution, could be better. So if this is the smallest volume that can be polymerized. However, when you move, if you can move more precisely, so if your piezoelectric stage, for example, has movement of 50 nanometers, then you are just moving this ellipsoid by 50 nanometers and then obtain smoothness on the top of it in this range. So even this voxel is not so small, you can obtain very smooth surfaces. And especially there are a lot of techniques that can improve smoothness, like annealing or reflowing, or using some chemicals to make it even smoother. So in practical experimental setup, it looks like that. This is the idea. So this is our system, inverted system. So we have piezoelectric stage, inverted microscope, and then the power of the laser is controlled by acousto-optic modulator. Yeah, and everything is controlled by software. This is our system. It's not, let's say, custom made. It's commercial. So from a company called Nanoscribe, and then they provide a lot of this type of machines. And our machine has a piezoelectric XYZ stage, translation stage, to obtain movement of the sample. But yeah, there are a lot of other concepts which are even faster. Some have some advantages, or these are also disadvantages. So for example, instead of moving whole sample on piezo stage, you can move the laser beam with using galvanometric mirror scanner, and then you can improve by order or 2 orders of magnitude speed of writing, but you need more powerful laser, of course. And yeah, so you can see example of really impressive high ratio structure, which is 20 micrometers wide and 500 almost micrometers in height. And yeah, people are improving it even more. So for example, when you use resonant galvo scanner, so in that case, this micro mirror, it's not resonating in one axis when you want, but rather it's constantly resonating with its own resonant frequency. So the laser beam will be scanning all the time. So to achieve different exposure, you use Pockle cells, which is then synchronized with this shaking mirror, and with that you can get even more speed. Or you can use digital mirror device when everything the light is deflected just by one small device. So yeah, here is the comparison of the systems. So as you can see, there are a lot of stepper motor side, piezo, digital mirror device, galvo mirror, and this is the fastest one. It's from that time it was resonant galvo mirror, which is pretty, yeah, it's 8,000 millimeters per second. So when you compare it to our system, which is about 90 micrometers per second, so the difference is absolutely huge. So I will be talking also a little bit about printing time, but our structures are printed in 3 minutes. And we are printing through the whole night 1,400 of such structures on our sample, just to cover all the sample. So you can imagine with that, with that newest version of this product, you can do that in 3 minutes, not whole night. So this is quite impressive. Yeah. So the field is dynamically developing. And it's very interesting in itself as well. So, but we are interested in applications. So we are not, let's say, users that are developing the machines, but we are rather developing the what we can produce with existing ones. So yeah, what people can produce now using that technique. So pretty intermediate size structures, like here in millimeter range, which are quite strong because they can withstand the weight of the coin. Any arbitrary shaped devices like robots, or I don't know, just for fun. And of course, when you don't want big volume, you can focus on small details. And here, as you can see, this line, it's about 200 nanometers, and this is obtained by using carefully chosen power and chemical additives to the resin, so the polymerization occurs only in that place that you want. And of course, it's not only for the architecture, but I must say that architecture is most impressive one. So here is the castle on the top of the pencil. So you can print on different substrate. This is very, very important in that technique. So it's compatible with almost everything, and it's rather difficult to remove the thing from the substrate than to put it on. Yeah, this is another architecture part, but it's so beautiful that I can't resist to put it here. Okay, and so why we are interested in such a thing? So what people can do that? So micromechanics, for example, this is very interesting example. So people were printed the ball on a spring attached to this kind of block, and by using optical tweezer, they were able just to measure the force of this spring, and yeah, it was pretty breaking in that area. Another interesting micromechanics is that in nature, as far as I know, there are no bulk objects that when you squeeze them, they are twisting themselves. I mean, bulk materials, and only some structured materials can behave like that. Because usually, yeah, when we squeeze something, it just goes on the sides, right? It's not twisting by themselves. So by this direct laser writing, you can produce this impressive structures that when are carefully designed, you can obtain different torsion, different twisting. Yeah, so another micromechanics, which is even more impressive, the field is amazing. So you can print such a grabber on top of optical fiber. So here is the top of optical fiber, and thanks to the careful design of this disc and this area, you can turn it on or off by light. So you are just putting light to the optical fiber, and during that your grabber is opening or closing. So you can, yeah, you have optical grabber, but let's say in micrometer, so in larger scale than just optical tweezer, and much more heavier objects you can grab. Or this one, it's absolutely beautiful as well. So you have, and then the people showed here that they have 2 rotors and with 6 handle points, and they grab these rotors by optical tweezer, optical traps, and so they can rotate them. And by careful examination of the field, rotation field that they will obtain, they can produce hydrodynamic vortices, or just good enough liquid flow that they can move in any direction as they want some small particle like here. So this is also quite impressive. And of course, last but not least, this resin, as you have seen, it's transparent. So you can produce optical elements. So here are examples of freeform mirrors, multi-layered objectives, microscope objectives, so 2 layers or even 3 layers. And this one is attached even to an optical fiber again. So you have ready probe for some diagnosis or stuff like that. And what more? You have a lot of photoresist that you can choose of. So for example, you can choose that you would like to have conductive photoresists, and here is some example of conductive puffs. People are obtaining that in many ways. So they can add metal particles to the resin, they can add they can use polymer that is conducting itself. People are adding also magnetic particles to that resin, and this is very impressive because they obtained such a rotor that can be excited by external magnetic field, and it's spinning. So yeah, maybe I will show you this one because I think it's quite beautiful. Micro turbine. Yeah, could you see something? Not yet. Stop share. This is not that window. I will manage. Yeah, this one. Sure. Okay, so once again, because it stopped. Oh, okay. I have this beautiful circle that tells that something is not okay. So maybe once again. Okay, once again. So stop sharing. Yeah, that's always nice. I'm doing my best. It's closing.
No
okay.
worries. It's fine.
Yeah, I'm almost there. So it's very close to the success. Micro turbine. Yes, I can see it. So now you will see it in a moment. So I'm start sharing. Yes, it rotates. So yeah. Okay, so yeah, it's not, for me, it's quite impressive. It's real time. It was recorded in real time. So typical frame rate, and yeah, it's just spinning. No electrical parts, no flow, no. Yeah, that's. I hope it was worth waiting a little bit. And so now coming back to the presentation. And of course, you can add, you can choose from variety of photoresist also in terms of biocompatibility. So people are, for example, producing scaffolds for cells, so to grow cells in some direction, or yeah, so to study them. You can put optical dyes into the resin, so you have fluorescent resin. You can change the Young modulus by adding some additives to the resin. And last, which I will focus a little bit more, it's the refractive index that you can choose from. So on the left side, you can see the examples of few photoresist resins from this company Nanoscribe and one from Ormocorp. And yeah, the refractive indices are changing from 1.58 to 1.5. But by changing the dose that you use for polymerization, you can obtain the gradient in the same resin. So this is quite nice. The people were printing green lenses and green waveguides for light with that. This is another example from, let's say, more biology field. So this is the phantom cell. So this is printed with different power object, which is in size of the typical cell. And by making some holography techniques, using holography techniques, you can determine the refractive index. And as you can see, this phantom cell, you can X-ray it, right? You can go, see what's inside, even it's a solid object. It's not like that. It's just a whole cell. So you can test the resolution of the holography, and then you can determine the refractive index and the content of the cell liquids inside. And last but not least, it's very recent paper. They called this resin nano ink, but in fact it's the regular resin, but we've added zirconia inside, so zirconium nanoparticles. And because of that, you can obtain a refractive index as high as 1.6 or 1.62, something like that. So it's, yeah, higher refractive index. But there is whole branch of science called high refractive index polymers. And so again, just you need to read literature and find out if there is something new, because it develops rapidly. I mean, every 2 months there are few more papers about new resins. And yeah, so this is our photonic nanostructure facility with the head of Piotr Wasilczyk. So of course there's orange light, and yeah, my friend Łukasz Sienkiewicz is the main power of printing, and yeah, the main expert in printing and working in our group. Yeah, and so yeah, from our field, they were showing, for example, nice photonic filters. So by changing the height, distribution of the such micropillars, nanopillars rather, yeah. So on the border, you can obtain different colors in transmission. So, for example, they mastered as well printing on the top of optical fiber. So yeah, that's something that we can also print as like lens or some other shapes. And the recent work, it's even coupling 2 optical fibers together with a printed optical waveguide and some microresonator here. And yeah, they were able to measure all the resonances, simulate that, and with success. Okay, so now it's time for results. So the first part will be about structures for light extraction. So I'm from the field of quantum dots. So so my basic area research were quantum dots. So quantum dot is a point-like emitter. We can think about quantum dot like point-like emitter. And so let's consider point-like emitter. But of course, keep in mind that point-like emitter, it's much broader term, because nanoparticle, it's also good point-like emitter. Nanolaser, which is 300 nanometers cube, it's also a very good nano emitter. What is even more interesting, the transition metal decalcogenide single flake, which is 10 micrometers or 50 micrometers in diameter or in characteristical size, could be also point-like emitter if the rest of the structure it's much bigger than this emitter, right? So it's everything about the ratio of the sizes. So in my case, I will be talking about quantum dots, especially self-assembled quantum dots. So such a point-like emitter emits light in all directions. So yeah, that's easy. And for simplicity, because we are usually interested in optical measurements, half of the light it's usually lost due to just because it's not going to your direction. Of course, we can improve that using some kind of mirror on the bottom, but usually when you don't have Bragg mirrors on the bottom of your structure, then half of the light is just lost at the beginning, so we are forgetting about it for now. And yeah, so, but the problem starts when you put such an emitter in a semiconductor matrix, so in a substrate. And that's because such a quantum dot, even it's almost on the surface, it's in fact 50 nanometers below. And because of that, you have total internal reflection, which limits the amount of light that can be extracted from such an emitter. And yeah, so when we compare the 2 pictures, these pictures comes from ray tracing simulation. So yeah, we can count just rays, and as you can see, yeah, most of the light it's totally internally reflected, and the only light which is coming out is light from this cone. So right, because this is reflected part, and this is the when they are not reflected, they are emitted upwards. Okay, so this is a problem. We have photon loss, which we don't want to have. But we can, yeah, use this idea of printing something on top. So we can put some medium that has intermediate refractive index, like 1.54 on top of such a semiconductor with a refractive index of 3. Yeah, solid immersion lens, we can call that solid immersion lens. Of course, it could be produced also with semiconductor as well, but then it will be produced with subtractive techniques, but this one is with additive techniques. And because of that, we have a smaller difference in refractive indices on the border. And because of that, this angle, it's bigger than the previous one without any additional optical structure. And we have more light extracted. And such lenses applied for quantum dots were showed quite recently. Yeah, they can target, aim at some interesting quantum dot like here, print this micro lens, and they obtain twice as much signal as before. Okay, so yeah, you can say that problem is solved, but unfortunately, unfortunately, it's not solved, because as usually, even if you have quite a lot of light, then you have to measure it. So you need to collect it to some device that will tell you how much light was coming from your quantum dot, your device, or other point like emitter. And we are usually doing it by using just regular optical microscope. And as you can see from that picture, it's not very optimal in terms of collecting light. You need, yeah, for people who are not familiar how it looks like in laboratory, yeah, this is how typical microscope objective looks like. This good one, I mean, expensive one. And there are few things that we should focus on. So typical microscope objectives has parameters like magnification, numerical aperture, working distance, and of course price. Let's forget about some numbers and focus only on these two columns: numerical aperture and working distance. So yeah, to remind it quickly, so this is example of numerical aperture 0.55, which results in working distance from the sample 13 millimeters. So this is pretty okay, because it's yeah, thumb-like distance, so you can, yeah, put your thumb under the microscope and squeeze it with it if you are not careful, stuff like that. So it's easy to use, especially if you have cryostat or stuff like that, when you have thick windows, or you need to, for example, put some microwaves to your structure or additional structures. But yeah, you can buy more expensive objectives, so it's great. As you can see, this angle increases from which you collect the light. However, working distance now decreased to 6 millimeters. So it's still pretty okay, but okay, when you really want to collect most of the light, you buy microscope objective 0.9, but then working distance is only 1.3 millimeter. So now we can see how it works. And in some applications, for example, in low temperatures, when you have such an optical cryostat like here, you would like to measure in liquid helium, or when you are doing EPR, so electron paramagnetic resonance, and you have such a big magnet, there is no option to put microscope objective inside, because you have just no room for doing that. And microscope objective is metal, made of metal, most parts are metallic. And similar situation is with high pressure anvils. So of course it is possible, but it's quite difficult to have the best quality microscope objective really close to the sample. So this working distance is pretty important. And last but not least, people are also measuring in really high magnetic fields, like you can see this is the pipe for cooling. If this picture comes from Grenoble, and in such a case, anything which is metallic, it's rather not allowed, and especially if you are measuring in pulsed magnetic field up to 100 Tesla or even higher, then metal is forbidden. Okay. It's not forbidden again, but you need to really carefully design all the stuff. And as well, you have little space down near the sample. This is example, 2 centimeters. So it's no option to put this such a big optical microscope. So how to not lose photons? Okay, so yeah. So micro lens will help because you obtain 50% more light, but still maybe you can do better. And of course you can do better, and this is the, let's say, our solution to that problem. Because if you are using 3D printing for making micro lens, so there is no reason why you shouldn't make different shape than hemispherical. So yeah, we propose just simple elliptical microlens. So this is the simplest modification you can think of. And as a result, from that area, you obtain perfectly collimated beam. This is the simulation. And some stray light going on other side. But you can compare these pictures directly because they are from ray tracing. So the number of rays here corresponds, yeah, it corresponds to the intensity of the light. Okay, so this is our solution that I would like to tell you more about. So it looks like that in microscope, scanning electron microscope. So the typical size of such a microlens that we are producing, it's 15 micrometers in diameter. Yeah, and we are printing it on everything. So I mean, on the glass is perfect, on some semiconductor surface is perfect. There was more problem on transition metal chalcogenides, but I will tell you later about that. Yeah, so as I mentioned before, the printing time is quite important. So we designed it, this microlens, to that it could be produced, printed in less than 4 minutes per one. So it's pretty okay. Then that's why during whole night you can print 1,400 of them on a sample. Yeah, it's not obvious how to obtain such an improvement in speed, so reducing the time needed for production, because the default slicer, so because the workflow is like that you design something in CAD software in your computer, then of course load it to the software from producer, and then you read that it will take 2 hours to print such a microlens, or half an hour, and then you're crying because you can't print 1,000 microlenses. But fortunately, there are a lot of tricks that you can use to make manually process faster. So for example, you can reduce the accuracy inside the microlens, because it's not needed to have this perfect smoothness inside the microlens, because this is the polymer, and it will finally polymerize with all the neighboring resin as well. So the only needed part, which should be smooth, is the upward, the outer shell of microlens. So for example, this method that we used, it's printing outer shell few times. So we are repeating the process of printing around the edges, and we are doing only rough polymerization inside the microlens. This is the one improvement that you can make. Another is, for example, that typically this software turns on and off laser after few hundred of steps, just to totally closes the shutter and opens it. And somehow the shutter is very slow. And for example, how you can improve the process, you can just order to the laser to have power equal to 0, which is much faster, because then you are using acoustic optical modulator, which is very fast, and you are not using some kind of mechanical shutter, and that will increase again your speed. So yeah, you can, as a result, you can print such a microlens in 3.5 minutes. So this is the result of simulation, of FDTD simulation, how the emission will look like in polar plot, and note that this is the logarithmic scale. So this is the intensity of the light on the radial axis, and on this angular axis there is numerical aperture or the angle of emission. And when we compare the blue line, which is elliptical microlens, to the spherical one, so the standard one, so you can see this one was pretty equidirectional, so equidirectional, so it will emit light in all directions as we expected. This is logarithmic scale, again, I remind you. And microlens, which has shape of elliptical shape, results in such a very sharp directed emission into numerical aperture. So total emission is below 0.1 numerical aperture. So this is very directive emission. So you can compare it the same, let's say, integrate. You can integrate that plots as a function of angle, just to see, for example, how to read that. If we have pretty poor microscope objective, like here, 0.5. So this corresponds to collection half angle of 30 degrees. So without microlens, this is amount of light that will be collected totally. With spherical microlens, we can see this doubling of the intensity of light. And with elliptical microlens, we can see quadrupling of intensity. But what is the most important, if you have really poor microscope objective, let's say you don't have any microscope objective, then maybe not any, but let's say conventional lens, just a conventional 1-inch lens, then you are in numerical aperture in that area, and you still obtain the same amount of light as for microscope objective 0.75 numerical aperture, so expensive one. So yeah, to see how it works in a real life, let's say, this is the plot of photoluminescence intensity collected only with one lens, obtained from transition metal dechalcogenide flake. This is the tungsten diselenite, covered with, was heterostructure, so it was covered with hexagonal boron nitride. And this gray curves represents the photoluminescence multiplied by 15 without microlens. So as you can see, it's barely visible, so you can't see anything. And with microlens, you have pretty nice signal. It looks like that. This was, as I mentioned before, this is, let's say, in the size, it's 5 micrometers of our flake, like here, covered with this hexagonal boron nitride. So this is not point-like emitter in comparison to quantum dots, but still, when you print such a big microlens on top of it, this one was 15 minutes or 30 minutes, I don't remember exactly, but then you obtain, everything works as you expected. So the gain is 450 times. So this is not 2 times gain, but it's much, much more. Another example is with quantum dots, which I really like. This is the system cadmium selenide, zinc selenide quantum dots. And again, without microlens, this is this gray signal. And blue one, it's with microlens. And this is here very important, that you can see single emission lines, sharp single emission lines. So so maybe, here I will tell you.
I'm very sorry, Aleksander. I'm very sorry for interrupting you. There's a question by Dr. Anton Samusev. Yes, Anton, please welcome.
Hi, do you hear me?
Hello.
Hello. So, my question is the following. I'm sorry for interrupting, but before you go further, so as far as I understand, the design of your lens has to depend on its refractive index. Since your resist has a dispersion, so the performance of the lens has to degrade with the wavelength. So to what extent your performance is stable when you go away from your optimized wavelength?
So it's it's surprisingly good. So as you can see here, The tungsten diselenide emits in 750 nanometers. So yeah, in close to infrared, near infrared. And cadmium selenide quantum dots are in 560 nanometers. And we do not need to redesign the shape, because in that range the changes are so small. So in fact, we can't see measurable difference for such a big range, and we think it's big. Yeah, it's because limited optical path in microlens, because these microlenses are very small. So this chromatical aberrations are not so important in this scale. That's so. It's okay with the answer, or I should elaborate more? Because yeah,
I think so. Thank you.
Okay. So yeah, as you can see, there are sharp lines from quantum dots, and yeah, I would like to underline here, to stress that that is the experimental setup. So this is the sample. There is nothing here. I mean, we don't have microscope objective here. We don't need it anymore. And there is single lens just in front of monochromator. And with this experimental setup, we can measure single quantum dot. So the object that has 5 nanometers in size, right? And what is even more important, we can come back to the same nanoscale object, because microlens itself, it's quite big. I will elaborate that a little on that a little bit later as well. But yeah, for me, it is very, as an experimentalist, it's very appealing, because you can measure something which usually is very difficult. For example, it's very difficult to come back to the same quantum dot if you don't have markers and you don't have some experimental setup that will allow you to precisely determine where these markers are. And here, if you print only one microlens on your sample, for example, and there is a quantum dot under this microlens, then you can, without any additional equipment, measure it again and again and again, and you can easily find it, because this is the only place on the sample that will have strong sharp line. Okay, so how to determine how to compare the experiment and simulation. So here is the plot of knife-edged measurement. So it means just that we put a knife edge into our beam, and we mechanized, and we are putting it into the beam and recording the intensity of a light. And yeah, because the beam was Gaussian shaped light, so we know that integral only on one axis will result in error function. And this is exactly what we observe here. So this is the measured error function and corresponding Gaussian distribution of our beam. And from that, we can determine the parameters. So indeed, we obtained half-power divergence angle below 1 degree. So this is ultra narrow emission from that quantum dot. So all signal comes into that angle, which we can translate to the working distance of half of a meter, so 500 millimeters with 1 inch lens, collective lens. So yeah, so half of a meter. So we increased from 6 millimeters to 500 millimeters. And so, yeah, question. No? Okay, it was just waving hands. Good.
I'm very sorry, yeah.
No. So this is now our example of quantum dots. So this is example of single quantum dot cadmium telluride without any magnetic impurity. As I mentioned before, we love magnetic impurities. So this is single quantum dot with single cobalt ion. So as you probably can guess, it's quite difficult to find exactly such a quantum dot. So you have billions of quantum dots on a sample, and you are looking only on quantum dots which has one magnetic impurity inside. And you recognize them by characteristic fingerprints, like this 4 emission lines with characteristic intensities. which is nice, but then finding again the same quantum dot or measuring it again in different experimental setup is almost impossible. And here, because this quantum dot is in a marked position by microlens, you can measure it easily. So this is the cadmium telluride system, this is cadmium selenide, so different material, as you can see, and again, answering the question about chromacity, about chromatic aberrations. This is again 664 nanometers, and this is 520 nanometers, and everything works with the same design. So we can't tell any difference between the performance. And this is the last example, a quantum dot with ion inside. And so here is example scan in magnetic field from 0 to 10 Tesla. So so this is from 0 magnetic field. These are these two lines, and as you can see, we can trace them easily, which sometimes is difficult, but here with microlenses it's quite easy. And simulation confirms that that it was quantum dot with single ion, and it confirms that polarization is conserved. So this sigma plus and sigma minus is still sigma plus and sigma minus, and we can't tell the difference. I mean, as far as we can measure, it's conserved, so it's not destroying the polarization. So now I'm coming to the end of that part. So as we can also put some modifications, so introduce some modification to this design. So the simplest modification is that to rise a little bit this elliptical microlens, and because of that, you will obtain a focus point not in the infinity, so not collimated beam, but focus in the range of 60-70 micrometers. And when you calculate beam width and focus position, it means that you can couple to an optical fiber, for example. We can produce such a holder and couple to a optical fiber, but about that in a moment. And last but not least, there are of course possible further improvements. So for example, recently there is a very, very nice paper on arXiv that people are also trying to use this stray lights, which are here that you lost because of this curvature of that surface. So you can produce this kind of structure, which is totally internal reflection lens. And because of that, you can reflect even those light which is lost here. So, and they produce that, and indeed they see improvement, so it's really good. The only disadvantage is that you need faster equipment, because the volume of this structure is much bigger than volume of this simple microlens. But still, it's very simple, and you can use it. And as I mentioned before, all this could be applied to point-like objects, and it depends on your scale that you're working with. But point-like object could be perovskite, could be nano laser, could be nanowire, could be quantum dot, could be nanocrystal, stuff like that. Okay, and so the summary is that we can measure without microscope objective, but we can measure nano object without microscope objective. So this is quite nice. We have this photoluminescence gain in collecting light, and we have working distance larger than half of a meter. And the second part is optical fiber coupling. It's much shorter, so don't worry. So when you have semiconductor photonic devices, there are listed some examples, but of course they are semiconductor photonic devices are not limited to those LEDs, voxels, SESAMs, sensors, and stuff like that. You need somehow to measure them again, and if half of a meter it's not enough, and you are measuring things that are more complicated, that you cannot easily integrate, like transition metal dechalcogenides or some fancy optical measurements, then you need somehow couple it to the optical fiber. For example, to put it to this high magnetic field magnet, or to send it to the other laboratory when equipment that you need is there. So you can couple your photonic device from free beam using such a macro stage with a microscope objective, right? And it works okay, but it's not small. Definitely, it's not small. So you cannot put it inside your magnet, something like that. Of course, you can use micro positioner. So this is a better solution. Like this, put it on AttoCube and try to find out the interesting object. But let's say the ultimate level of miniaturization is just coupling it to the optical fiber in integrated way, let's say. So this is an optical fiber. Here is some groove which is cut on a sample. So you can put optical fiber here, glue it everything together, and then you have nicely positioned optical fiber, and you can couple it to this the laser or other stuff like that. It's okay, but as you can see in the right upper corner here, this cutting grooves, it's sometimes, or etching grooves is again a subtractive technique, right? So we can, we were thinking if it's possible to produce that, to make it the integrated coupling in some more convenient way and less invasive for the sample. Especially transition metallurgical cogenite samples are very, very fragile. So cutting it like that on here, it's impossible because of this fluid and speed and stuff like that. Okay, so how optical fiber coupling works? So we would like to just put optical fiber near to our emitter, which is pretty simple, right? But usually it looks like totally different. So you are shaking. Sorry. So you are shaking. You need somehow to glue it at the end. So we are looking for a solution that will compensate initial misalignment of our optical fiber because our precision is limited. And of course, we know such a thing from chemistry or from our kitchen. It's a funnel. So we need a funnel for optical fiber. And it's called in a cosmic industries called drogue. So we are looking for a drogue. And yeah, with optic of 3D printing, we can imagine that we can print something funnel-like shape. Of course, as I mentioned before, the printing time, it's a limiting factor. So we would like to think somehow how to reduce the volume of our structure. So if we want bigger initial misalignment tolerance, then we should produce bigger structure or, of course, wider structure with this angle, which will be higher. No, yeah, but this is time cost. The time cost is quite high. So to reduce the volume, we can, let's say, cut it here. I mean, so we could not print here, and we will gain something more. So we will gain the flexibility as well. So it will work as a spring then. And springs are pretty nice because then they can redirect our optical fiber to the center of optical emitter. And last, how to reduce the volume. We can take the inspiration from the nature, so we can make the least possible amount of this segment, so 3 of them will be sufficient. So yeah, so this is our design of such an optical fiber port. So we call this docking drogue cone, alignment collar, which is in diameter of 125 micrometers, so the typical optical fiber. And here is the waist, and by tailoring this waist size, you can tailor the stiffness of your spring. So this is our CAD design, and this is our printed results. So yeah, as you can see, they are in agreement. And now, yeah, now it's time for another movie. So I hope, again, it will work. So be patient just a little bit. Yeah, so here it works. So here's pause. And now share. And yes, this one. Okay, so this is this optical fiber port. And this is the consecutive animation made of photos from scanning electron microscope, about 800 of them. when we are putting optical microfiber to our microport. This optical fiber is covered with gold. As you can see on this right side, there are scratches. So we just scratch the gold, but it also, and this, as you can see, the structures are not only straight, but a little bit curved, which proves that this spring-like action works. So indeed, it was redirected towards the center of this structure. We also printed here some supportive structures like this ring around, just to improve adhesion to the substrate, because it's a very big structure. And this cross-like target inside in the middle, just to evaluate the precision of this procedure. Okay, so now it's time for stop sharing and back to sharing a presentation. Okay. Yeah, so this animation was done in this AttoCube experimental setup. So you can see this is only short part of optical fiber, and when you are carefully looking, you can see that 3 of them are visible even with a smartphone camera. So there are 3 such optical fiber ports, and we can dock to each of them. And everything was covered with gold because in scanning electron microscope, we don't want the accumulation of electrical charge. Okay, so how to measure that? So we put the optical fiber on a 10 centimeter arm or standard Thorlabs XYZ stage, which has quite large crosstalk. It is plus minus 5 micrometers. So when you use this screw, then 5 micrometers plus minus 5 micrometers can be on different axes. So it's pretty standard experimental setup. And we put the microscope objective with camera on the bottom of the structure. It was printed on a glass, and we introduced the light into the optical fiber, and then we were observing the bottom of the structure with microscope. And this image looked like this. So this big red area, it's the optical fiber. It was illuminated. We additionally introduced some light into the core just to see the core, to the cladding. And the core is this brighter spot inside. And we were measuring with machine vision what is the position of this bright spot in XYZ, in XY coordinations. And these are results of 46 consecutive put-ons and put-outs. So we made that 46 times without stopping. Each, let's say, introducing optical fiber was about 3 minutes. So it takes 3 minutes to fully dock in and then dock out. And yeah, as you can see, this precision is pretty good. It's FWHM. Is well below 120 nanometers. And what is interesting, this is much below the error that manufacturer of fibers provides. So the error of positioning core inside the optical fiber, because when they are producing optical fibers, the core isn't exactly in the center. There is some misalignment as well. So this error during the production of optical fiber should be smaller than 500 nanometers. So we are well below that level. So let's say, yeah, it's even better than just error during manufacturing the optical fibers. And we tested it in low temperatures because we are interested in semiconductor business, right? So this is example of glued with ultraviolet resin optical fiber. It's here to our sample, and this is the droplet of a glue on top of it. This glue was again photosensitive glue, so the procedure was like that. We just docked optical fiber to the sample, then put a droplet of a glue, illuminated it with ultraviolet light, and then everything was cured. and stable, so we could attach it to this metal probe and put it into the helium dewar. So we had big helium tank, and we were putting it in and out. Each cooling cycle was below 5 minutes. So from room temperature to liquid helium temperature in 4 minutes, just to avoid boiling out all the liquid helium. And the results of photoluminescence are shown here. So the intensity of photoluminescence on a quantum well, this was example with a quantum well, well, yes, it's below 2%. Sigma was below 1%. So from that, we concluded that it's not falling off. I mean, it's not detached from the sample. Everything it's firmly glued. And what is even more nice, that we were storing it on our shelf about 6 months, and then measured it once again, and everything was fixed. I mean, so it withstands 6 months easily. We don't know longer period, but 6 months was tested. Okay, so summary of this part. It was much faster. It's that, yeah, direct laser writing, it's good for prototyping, because this is example of a prototyping coupling, right? Because if you are aiming to your final application or final device, then of course you can make some grooves and prepare your substrate in a more fancy way, or increase these technological steps that you need to couple optical fiber to the structure. However, when you are in a rush or in just a laboratory and you don't have time, then you need to, yeah, to work on your own. And then such a prototyping, it's really nice because you can quite fast change parameters and experiment with them. And it was interesting for us that this resin photopolymer, it is IPL deep from nanoscribe, withstands low cryogenic temperatures pretty well. And we obtained this accuracies here. Okay, so it turns out that as well, people were following up this research, which was really nice. So for example, they were printing such a micro connector on a cover glass and then print micro lens on the other side. So you can use it as a device with micro lens. And even more, I've mentioned before that in this paper, they were producing this total internal reflection improvement of our elliptical microlens. So they also printed full compatible system that can couple to this new design with optical fiber. So they have chosen 2 lens scheme. So this is the first microlens, this total internal reflection one. And here they printed on the top of the optical fiber another microlens, which is 100, 500 micrometers high. And with that, they obtained collimated beam and then collimated and then focus it into the core of optical fiber. So this is really, really nice paper. I like it. And how it looks like in real life. So these are images from optical microscope. And again, this inserting the optical fiber is pretty easy. Here. And they were measuring them as well in liquid helium, bath cryostat, similar to ours. So with UV cured resin. This is the ATMO stack and the probe. It was in helium bath cryostat, and they were measuring quantum dots, single quantum dots on that. Yeah, so this is the total summary of my talk. So I hope I convinced you that direct laser writing is pretty cool. So you can use it in different applications, especially micro optics, micromechanics, and it works well with cryogenic temperatures. And yeah, we showed with these micro lenses that you can have spectroscopy of single nano object, but without microscope objective at all. So it's pretty nice, and you can attach to it optical fiber as well if you want. Yeah, so yeah, thank you for your attention.
Wow, Aleksander, thank you very much. I was amazed all your talks, since I've noticed that it's like 159 slides, but it all went very fast and smooth. So thank you very much once again from all the organizers. So we have time for discussion, and I would like to start from Dr. Andrey Bogdanov. Andrey, please.
Yeah. Alexander, thank you very much for the fascinating talk. So I have a question about the behavior of the polymer that you use for nanofabrication in the medium infrared range, like let's say 3-4 microns. Is it transparent, or there are some resonances?
Yeah, of course. So it would be something around 163. Okay, so it's somewhere here. Okay, so let's start with your interest. Oh, yeah, in this. So this is transmission that we have measured to 2 microns. So it's pretty good. Oh, so here is maybe your absorption as a function of energy. So I guess it's okay. This answer for your question, or should I elaborate somehow? I don't know, because we haven't measured in such a range, but people, okay, so I can elaborate. So people are usually printing devices in this infrared range, so 1550, right, or 1300 or stuff like that, where there are these telecommunication windows. And they are using this resin with success, so they are not complaining. And they are, for example, also using it to print the photonic wire bonds between 2 optical fibers, right? So there are 2 optical fibers, and they are just connecting the fibers between them on a chip in telecom range, yeah. But I don't know farther in 3 micrometers. I don't know, because we don't have experiment set up for measuring it.
Okay, and the second question: did you think about using not the bulk lenses for light extraction, but maybe meta surfaces? It's also like a flat stuff.
Yes, we were thinking, but people already have done it. But the problem is that they are usually not focusing. I mean, they are good in extracting light because they increase this by resonances and stuff like that. They increase somehow extraction, but then it's unidirectional. Or if they can use it, this is called, I guess, ultra flat lenses or something like that. So they are just printing like a Fresnel rings, but even smaller, like antennas or stuff like that, covered with gold. But they only showed the focus point, which is in range of 100 micrometers from the surface. I don't know why, if it's too difficult to obtain collimated beam, but yeah, but as a result, I have seen only papers when they were in the range of 100 micrometers, the focus point. So if you are interested in coupling to the optical fiber, I think it will be okay. But when you are targeting to no optical setup at all, I mean this long working distance, then as far as I know, it's not already developed.
And the last question, so do you try to print something on the end face of the fiber directly?
Yes, yes. So this is, let's click here. No. Okay, so somewhere here I was showing so here is printed directly on the top of the optical fiber in the right corner. So this is optical fiber, and these lenses are.
Is it group lead by Dyson, yeah?
Yes, but we also have such, and I was showing here. This is from our group, so we are printing. Yes, the logo, microlens, other kind of So we can do that. Okay. And the last but not least, this is from this our department. This optical fiber that are connected with optical waveguide and microresonator.
Mm-hmm. I see. Okay, thank you.
Yeah, thank you, Andrey, very much. So we have another question from Dr. Anton Samusev. Anton, please.
Thanks, Gosha. So I've got a couple of questions. The first one, both about the TMDs integrated with your microlens. So the first one, have you checked whether TMD flake degrades under the with the interaction with resist? So
Yes,
have you
yes,
somehow
yes, yeah,
separated
yes.
those effects?
Yes, but I need, yeah. So, okay, this is example of our structure that we succeed, and these are pretty, this is before printing, so photograph before printing, this is after printing. So as you can see, we are starting with bubbles as well. So the bubbles, but it was due to the annealing. But the crucial things were, it's covering it with HBN in our case, because it turned out that our resin, so IP deep from nanoscribe, is interacting with flakes. But there is a paper from Manchester group, I think, and they were just making a droplet of a resin, micro droplet, but let's say comparing to our sizes, it was huge because it was half of a millimeter or in that range, and they were reporting that everything is okay. So that was different resin than ours. So exist on the market resins that are chemically different than ours and are not destroying the flakes. But in our case, even printing at the beginning on transition metal dechalcogenides covered with HBN were pretty difficult, because it turned out that quite important is the quality of this HBN around. So yeah, here are examples. So this is our very big flake on this dashed line, and we would like and covered with HBN, which is not very smooth and not very flat. And in the, exactly in the place where this flatness was destroyed, you can see that start to appearing big bubble during the printing, right? And after printing, yeah, the microlens was printed. However, this some destructive wave region appeared, and this is another example on the right side. So our flake is again dashed line, and we can see there are bubbles of resin, and probably due to changing the interference conditions. So the result, let's say recipe for good printing was just to have flat HBN, so you don't have really high steps of hexagonal boron nitride. So everything is flat, and we were also not printing just directly over the flake. So we just make small cavity, very small. It was just 1 micrometer high, which was unpolymerized. And then after all printing, developing and stuff like that, we were just shining ultraviolet light on that just to be sure that it was polymerized. And then no bubbles occurs and everything is fine. So yes, this is another finding of this paper in supplementary materials that we were, yeah, it was difficult. Let's say half of a year, it was just only optimizing that, but then it was obvious for us that it should be flat, and that's it, right? That was the key factor.
Okay, I see. Thank you very much. The second question, the answer will be probably negative. So have you tried to pull out the emission from quantum dots from TMDs? You've mentioned that you can obtain ones by indentation or nano-sized defects or something. Have you tried to extract this emission there?
Could you repeat? To extract light from transition metal dechalcogenides?
From TMD quantum dots.
Oh yeah, so not yet. No. Because our group starts on working with TMD's quantum dots, so we are not yet, let's say, on that path. Yes, so your correct answer is negative, not yet.
Okay, so
yeah.
Good luck with that. Thank you.
You're welcome. Thank you very much.
Thank you very much, Anton. So before I have a couple of questions. Before I ask them, I would like to send some promoting commercial post to the chat about our seminar. So please follow us on YouTube and follow our every week subscription. So I think I've sent it to the chat in the Zoom. So yeah, and I have maybe little bit naive questions, but maybe they're a bit general. So I wonder, when you mentioned your beautiful elliptical shaped lens, I wonder, have you tried to put some quantum dot or nanolaser, as you already mentioned, on top, I mean, under the lens? Or, I mean, just what are the fabrication steps? You first produce some quantum dots, some emitting stuff, and then you just cover them with the lenses?
Mm-hmm. Yes, exactly. So we usually have a lot of samples in our drawers. So because of MBE laboratory. So the, let's say, standard procedure is that we take a very small piece of sample with quantum dots, which is already grown by MBE. And then we put a droplet of this photoresist on top of our sample, put it to the printing machine, I mean to the nanoscribe writing machine, printed, developed in a solvent, which is PGMEA and isopropanol. And then when it's dried, we are measuring it. So this is the standard procedure. But for example, we were trying also to play with these printed structures in a term that we were trying to move them. I mean, when they are printed already on a glass or on a substrate, we were poking them from side just to see what will happen. And it turned out that we can move them on the sample. So they are just, if you poke hard, they will just move or fall down. So yeah, we can detach them from the substrate as well. However, when we would like to detach them deliberately, I mean, for example, clean the sample. So when you print it on a glass and now you would like to remove all of the printed nanostructures, we can't do that. I mean, we are trying even acids, quite pretty hard acids, and you know, probably the hardest acids will work, but the regular, quite mild stuff that will not destroy the samples, regular samples, will not remove the object. So if the object is detached mechanically, it's okay, but chemically, for example, we couldn't detach the microlens. So let's say last part of the answer is that Łukasz Zinkiewicz also could print on, let's say, on a carpet made of some polymer. So you take a glass, you put some polymer on top of it, and then print on that polymer. And this polymer, it's you can solve it with water. So as a result, you can detach printed structures into the solvent. So for example, in that manner, this our facility, this lithography facility, produced optical tweezer tools. So there are such balls with a sharp tip. So you can, for example, kill the cell or just try to poke the cell, organic cell or stuff like that. So it is possible to detach them from the surface, yes. But to print, let's say, to put quantum dot on top of microlens directly, we can't do that. And yeah, we can try if we have colloidal quantum dots. So we can invert the process and then spin the quantum dots on top of the structures. Yeah, that's possible.
Okay, yeah, thank you very much for this comprehensive answer. So, and maybe one more general question from my side. So when you were mentioning this waveguide coupled system, I wonder, is it more about excitation of some whatever light emitting stuff in the target, or it's more about the extraction of the excitation?
And yeah, this is another benefit or disadvantage at the same time of the system. So so you can benefit if you need to extract light, and you can benefit if you need to excite something harder. So example usage of it, of our microlenses could be, I don't know where it is, terahertz devices, because, okay, I don't know when I have it, so maybe I will just skip that. I don't know why here, but so the idea is that you have a nanowire, and you need to irritate it, to excite it with infrared light just to detect terahertz radiation. Oh, here, yeah, okay. So you need to excite it with infrared laser. And it turns out that usually it looks like that there is a parabolic mirror for terahertz, which focuses the terahertz, quite a wide beam, like, I mean, this is the real size of that beam. And here it's very small hole for infrared laser that will hit your optical, your nanowire here, just to make optical rectifying and stuff like that to detect this terahertz. And it turns out that this hole, it should be very small to not interrupt the terahertz, but it limits the optical numerical aperture of your infrared part of this experimental setup. And this is a problem because the people who are measuring told me that they are reaching the limit of ionization of the air. So their infrared laser is pulse laser, and it's on the full power just below the threshold of ionization the air. So in that case, exactly this micro lens on the top will help, because then you can gather the focus, so you can obtain extra focusing of infrared light on the nanowire from bigger area than just regular area. So the power density will increase without introducing any metal object or any big object. It will be very small, it will be not interfering with terahertz. So in our case, in quantum dots, it's quite tricky, but we usually have, let's say, a lot of power from the laser. So we are not limited by the excitation power, but we are limited by the extraction. So this part is more important. However, if there is problem with excitation, you can of course this part optimize for this part. Yeah.
Okay. Once again, thank you very much. So, dear colleagues, are there any more questions? So, if not, I would like to thank once again Aleksandr Bogucki for wonderful talk and very fruitful discussion. So
thank you very much.
Yeah, thank you. So very quick announcement. The following week, I think we're skipping the seminar. We don't have any talks, so stay tuned, follow us, follow our subscription. And probably in 2 weeks, we'll have a talk from Dr. Francisco Ortega Sierra from Department of Microtechnology and Nanoscience from Chalmers University of Technology, Sweden. So the topic is still to be announced. So with that, I would like to close the seminar and thank all for participating, especially Aleksander for a wonderful talk once again.
Thank you very much and for your attention.
Thank you very much. Yeah. Bye-bye.
Bye-bye.